This is the audio notes on how to do calculating thermal energy change. So the math that we're going to do with phase change. If you have this handout, what I'd like to do is go over it step by step, starting with students doing step number one. On the back of the sheet of paper, I'd like you to create the phase change graph for water. Again, label it X and Y axes, mark the relevant temperature since it's water, that being the melting point and the freezing point. So go ahead and take a minute to do that. As I'm moving along with the notes here, if you need to pause the video to allow students to catch up with the work, feel free to do so. Otherwise, this is what I am referring to when I talk about a phase change graph. For now, you can ignore the temperatures in red. That will come into play when we start actually doing the math. But remember, solid, liquid, gas are on the slopes. The melting and boiling are going to be on the plateaus. And that answers hopefully the question of why do we need plateaus? We need to show phase changes. Energy is not only needed to change the temperature of something, it is also needed to break up intermolecular forces. And that's what happens during a phase change. Going from a solid to a liquid, you break up the attraction between solids and liquids that hold it in a rigid structure, and going from a liquid to a gas, you break all remaining attraction. Let's get to the math things. Step number two, starting to do calculation. The main equation that you'll be using is Q equals mc delta T. That triangle means delta. Delta T is the change in temperature, the final temperature minus the initial. So if we know two different temperatures at which something is, so we're heating something up from 30 degrees to 50 degrees, we could figure out the change in temperature. The C value is referred to as the specific heat capacity. This is actually on the 4 bond types packet, but it is dependent upon the state of matter and what substance it is. Most of our thermal math will be involving water. M stands for mass, and Q is heat. And joules is our main unit of energy when it comes to heat. Besides this equation in bold, there's one other equation, Q equals M times H, where it's going to be the mass of the object, and multiply that by either the heat of fusion or the heat of vaporization. When it comes time for a quiz or a test, these two equations, Q equals mc delta T and Q equals M times H, those equations will be given to you, as will the constants. So if I look towards the bottom of the sheet, there is a specific heat capacity for liquid water of 4.184 joules per gram degree Celsius, of ice of 2.03 joules per gram degree Celsius, of steam 1.99 joules per gram degree Celsius, and then there's the heat of fusion of water and the heat of vaporization of water. Heat of fusion and heat of vaporization were also brought up during the 4 bond types packet last class. Typically, these values are given in kilojoules per mole, 6.01 and 40.79. However, to make life a little bit easier for you, I usually report them in joules per gram. That way you can just multiply the mass times the value to get how many joules were created, instead of having to do a mole conversion. So once again, Q equals mc delta T. Q is heat, mass times specific heat capacity, so how much heat can you absorb before your temperature changes, times the change in temperature. And Q equals M times H. Mass times either heat of fusion, if we're referring to going from a solid to a liquid, or heat of vaporization, going from a liquid to a gas. Now that I've gone over all the information on this sheet, we are going to do this practice problem on the bottom of the page. The problem says, if you are given 10 grams of ice at negative 10 degrees Celsius, calculate the amount of energy needed to raise the temperature to 110 degrees Celsius. This has a lot of steps to it. And what I did for this, as you will see in the homework as well, is I divided it up into different smaller steps, A through F. And that's going to bring me back to my smart notebook sheet. On your heating and cooling curve, I recommend writing down the temperature you start at and end at. The reason I'm doing this, notice that it is not one straight line between the starting and the ending point. Instead, there's a series of steps. Step 1 would be going from negative 10 degrees Celsius to 0 degrees Celsius. Step 2 is melting. Step 3, going from 0 degrees Celsius to 100 degrees Celsius. Step 4, boiling. And step 5, going from 100 degrees Celsius up to 110. Number one mistake students make when doing thermal math is they try to do it in one step of Q equals MC delta T. The problem is that C value, the specific heat capacity, depends on the state of matter. And here it's a solid, here's the liquid, here it's a gas. There's different heat capacities. I have to do more than one step. So what I'm going to do first is step A. I'm going to calculate the joules of energy needed to heat the 10 grams of ice from negative 10 degrees Celsius up to 0. So that would be doing this step right here. If I move on to my next slide, I would start by setting up Q equals MC delta T. Then plugging in my values. 10 grams is the mass. The C value of ice is 2.03 joules per gram per degree Celsius. And the change in temperature, my delta T. I end at 0. I started at negative 10. 0 minus a negative 10 is 10 degrees. That gets me 203 joules. A couple things to note here. First thing to note is that I'm not keeping track of my significant digits too much right now. I actually underline in red the second digit because this has 2 digits here, and if I used a decimal, this actually would have had 2 digits as well. The thermal math that we're about to do involves the rules for multiplication for each step, but then at the end, as you'll see in a little bit, we have to add all the steps together. And we don't emphasize the rules of adding when it comes to sig digs. So we're going to be a little lenient when it comes to significant digits. Other thing worth noting is what I wrote down here. Note that the C value is used for ice because that's the temperature and the state of matter that we're in right now. So again, the hope is you're on the back side of this practice sheet. Again, this practice sheet right here is started with you drawing out a heating cooling curve, and we just completed step number 1. Now we are at a solid at 0 degrees Celsius. Any additional heat is not going to change the temperature. Instead, it's going to break its rigid solid structure. It's going to melt it. So step number 2, or part B rather, is calculating the energy to melt 10 grams of ice. Since there is no temperature change, I'm not using Q equals MC delta T. Instead, I'm using Q equals M times heat of fusion. Once again, to make life easier, I can report this in joules per gram. So 10 times 334 is 3,340 joules. And hopefully you are following along and writing this down as we go. And as I mentioned underneath my math, I make the point that melting is breaking that lattice structure, that rigid structure of where solids are vibrating in place. It takes a lot of energy to break them up. So, you've now done 2 steps. You've calculated how much energy is required to go from negative 10 degrees Celsius to 0, so to heat up our ice, and you've calculated how much energy is required to melt our ice. Now we are in pure liquid water at 0 degrees Celsius. We need to increase the temperature to 100 degrees Celsius. This is the 3rd step right here. So this is where I'm going to solve for 10 grams of water, heating from 0 to 100 degrees Celsius. Since there's a temperature change, I can now solve for a delta T, which means I can also do Q equals MC delta T. So what I'd like to do is take a moment, and again, you could pause the video if you want, but take a moment to see if you can solve for this next step. Remembering that we are in a new state of matter. We are now a liquid. So we should use the C value for liquid water. That heat capacity of water is something we will talk about at the end of class as well. So take a moment, solve for delta T, what's the change in temperature, and then plug in and solve Q equals MC delta T. Change in temperature is 100 degrees, final minus initial. Plugging that into delta T, my C value is 4.184 for liquid water. 100 degrees Celsius is my delta T. The mass is always 10 grams. I get 4,184 joules. So we have done 3 steps. Energy to go from a solid at negative 10 degrees Celsius to 0 degrees Celsius. Energy to melt that solid to turn it into a liquid. And energy to heat up that liquid from 0 to 100. Our 4th step is the energy needed to boil, to turn that liquid into a gas. So we're solving for this plateau. "10 grams of water boiled." Since there's no change in temperature because the heat added is breaking apart intermolecular forces, I'm going to be using Q equals mass times heat of vaporization. I'm going to have this covered up in a box right now because I'd like to see if you can find on the front side of the sheet of paper the heat of vaporization value. Because as I mentioned before, you are not required to memorize these values. You simply have to know when to use them and how to use them in an equation. While you're looking that up, I'm also going to read the very bottom of the slide. It says the heat of vaporization value is a larger number than the heat of fusion. Because when you vaporize, when you go from a liquid to a gas, you are breaking apart all remaining attraction, all remaining intermolecular forces. And it takes a lot more energy to sever all ties, if you will, rather than just to loosen up the attraction. As for the math, 10 grams times 2,263 joules per gram. Once again, if students need to catch up from what I'm saying, feel free to pause the video at any point so people can keep up. But going back to our phase change diagram, step number 1, I heated my solid from negative 10 degrees Celsius to 0 degrees Celsius. Step number 2, I melted my solid, turning it to a liquid, still at 0 degrees Celsius. Step number 3, I had my liquid go from 0 degrees Celsius to 100 degrees Celsius. Step number 4, I boiled my liquid, turning it into a gas at 100 degrees Celsius. My final step is heating up that gas from 100 to 110. Part E, 10 grams from 100 degrees Celsius to 110 degrees Celsius. Reminder, use the C value for steam. Once again, feel free to pause the video so you can try to figure it out, and then I will reveal the answers in a second. Change in temperature, 10 degrees Celsius. Notice my C value is 1.99 joules per gram degree Celsius. That gets me 199 joules. I have now done 5 steps. Step 1, 2, 3, 4, 5. Or steps A, B, C, D, and E. I've figured out the amount of energy required to do each of these steps. 3 of the steps, right here, and right here, required Q equals MC delta T because in those 3 steps, the temperature is changing. However, on a plateau, the flat horizontal part of the graph, temperature doesn't change because energy being added is making the state of matter change. So there I use Q equals M times H. Once I get those 5 values, I'm going to add all of them up. Because if I add each part, it will give me the total amount of energy to go from negative 10 degrees Celsius to 110 degrees Celsius. When I do, I end up with 30,556 joules. Nice thing about the metric system is I can convert that to kilojoules, 30.556. And keeping track of sig digs, which is a little tricky because I'm using the rules of add subtract along with multiply divide, I rounded it to 30.56 kilojoules. Again, I would not worry too much when it comes to significant digits with this because of those rules. Again, if you need to pause the video to catch up with the work here, otherwise I have one last slide to explain. My recommendations when doing any problem like this, like your homework will be, is to always start off with a heating cooling curve to show your starting and ending point. Secondly, like I mentioned before, we are not going to be overly concerned with significant digits because they involve the rules for add and subtract, which we do not emphasize as much as the multiply divide. Third point, which I know for my students is going to come into play with the homework for next class. If instead of heating something from a low temperature to a high temperature, instead if you are cooling something, you're going the exact opposite direction on the heating cooling curve. So you would be going this way, which means your delta T's, your change in temperature, would always be a negative value. Since there's no change in temperature for a phase change, you would just report that heat of fusion value, 334, or that heat of vaporization value, 2,263, as negative values to show energy is given off. So if something were to cool, the change in temperature would be negative, as would the H values, the heat of fusion and the heat of vaporization. Negative values means heat is given off, an exothermic process. We are going to be going over this more in the next unit as well, but when you see a positive value for your heat, your Q value, that is going to refer to as endothermic. Heat is put in. For this particular problem, it was exothermic, however, heat was removed.